Any other questions from prior homework? Okay. What I'd like to do now is to introduce relative motion to you, and we'll spend a lot more time on it later on. Very important concept. So, relative motion. The best way to, if you get away from this stuff for a while, you'll forget certain things. But the best way, without grabbing a book and opening it up and restudying it, to remember this is I always draw some reference point, reference frame, and we'll use the traditional XY. And the description I'm going to give you applies for 3 dimensions, although we begin here in 2D to get a good understanding of this. And we have 2 points. 2 points. Let's call this point A. Let's call a point over here B. A and B. Now, we could define position vectors from the pole to each of those points. This is a position vector to A, and here's a position vector to point B. Now, what we're interested in is frequently a point related to another point, they might be moving away from one another, or they might be tracking on some relative path between each other. So if I would take and define position A as being made up of the vector to position B plus a vector now that goes from B to A, you can see the sum of these 2 vectors is equal to R sub A. The sum of these 2 vectors equals R sub A. And we need to come up with the notation for this. And so what I'm going to do is I'd like to emphasize that this is where we are going to position ourselves so we can make this a little more real to us. So we are going to be the observer here. And we're going to be watching what happens to point A relative to our position. The notation we will use for this, which is consistent with our book, is this is the position of A relative to B. That's the way we say that. The position of A relative to B. So you're the observer here, and you're looking over here. So the addition of these 2 vectors is equal to the position of A. Okay? Mathematics, pretty straightforward. Very simple so far. Now, this is a position description. Let's take the derivative. So the velocity of A is going to be equal to the velocity of B, and the derivative of a sum of vector quantities is equal to the sum of the derivatives. So it's the velocity of B plus the velocity of A relative to B. And finally, you can then take and develop the acceleration equation. And the acceleration of A is going to be equal to the acceleration of B plus the acceleration of A relative to B. So here are your kinematic relationships for relative motion, an introduction to relative motion. Is that right? Okay. So let's say that we have a vehicle that's traveling like this. Say this is, and I know its speed, let's call this vehicle A, and let's say its speed is 88 feet per second. That's an important one for you to know when you're on your motorcycle in particular or in an automobile. That's precisely 60 miles an hour. Precisely 60 miles an hour. If you do the conversion, unit conversion, it'll come out exactly 88. I frequently use this to convert in problems from miles per hour to feet per second. Okay? So that's 60 miles an hour. Now let's say we have another vehicle that is moving like this in a ratio of 3 to 1. Let's say it's moving at a speed of 50 feet per second. And we'll call this vehicle B, 50 feet per second. Okay? What I'm interested in is what the relative speed is. Now, where do you want to be as the observer? Do you want to be in the 60 mile an hour vehicle or this one moving slower? I want to be in the faster one. Okay? So we're going to be the observer here. Now, I didn't tell you where they are relative to each other. All I've told you is a description of their directions and their magnitudes. Okay? So if you have trouble writing the equation down correctly, then here's what I would suggest. Say that this is the location of A. Say that this is the location of B. And give yourself an axis system somewhere where you have some reference. So here's your position of A. Here's your position of B. Right? With some arbitrary reference point to get you to A, to get you to B. Right? So now I want this to be the observer. So which way do I point my vector? I want to be the observer here, looking at that one. So I'm going to go from here towards down there, aren't I? So this is going to be the position of B relative to A. And you can see the vector addition on the positions here. This vector R sub B, to get me down there, is going to be equal to the sum of these two vectors. So I would write that. R sub B is equal to R sub A plus R sub B relative to A. Think of yourself right here going for the ride in that 60 mile an hour vehicle. Then when you write your derivative, you'll get the relationship. Shown here. Let's put the parts in. Let's say that we've defined the traditional x and y, and why don't we use unit vector notation to describe the known information and see if we can get a handle on the missing piece. So the velocity of B is shown right here. And I want to relate this to the traditional x and y axis system. So how do I describe velocity of B? What's this hypotenuse here?
That's root 10. 10. Root 10.
So how much of this 50 feet per second is to the left?
50 divided by root 10.
Okay. It's 50 cosine of this angle, isn't it? Okay. And so it's 1 over radical 10 times that. Right? 1 over radical 10 times that. So what we do is we frequently use this. You may have used this in beam analysis if you took strength of materials. In trusses, doing truss analysis. Okay, very simple. And what you're doing is you're just simply scaling. If this is your 50, all you're doing is working up the scaling here, proportional to the 1 to 3 to radical 10, where that's 50. So this is going to be 1 over radical 10 times the 50, and this is going to be 3 over radical 10 times the 50. And be very careful to assign the proper directions, x, y, when you write your vector. Be very careful there. So you're going to assign a negative to the x component, and a positive to the y component. Equals the velocity of A, I like that one, 88I plus 0J, takes care of that one, plus this unknown relative velocity vector. So now all we do is solve for the unknown relative velocity vector. So we end up with the velocity of B relative to A is equal to this I component minus 88. So we have minus 50 over radical 10 minus 88. Somebody punch that on a calculator, it'd be useful. Plus 150 over radical 10 J.
Negative 103.8.
Okay. And 150 over radical 10?
474.3.
No.
Oops.
47.
My bad.
40?
47, yeah. I'll
47 point what?
43.
Units feet per second, I believe. Okay. Is that all right with everyone? Okay. So that means then, if we're the observer in this vehicle, we're heading down the road here. So we're heading down the road here, and we're watching this other vehicle that is going up this way. And what appears to be going on when I'm watching that vehicle over down there is it appears that I've got a big negative reading. In other words, it's really scooting away from me that direction. Really scooting away from me that direction, and at the same time coming up a bit. Okay, so a big X term and a positive Y term. Now here's something that's also that I would highly recommend. Instead of just cranking out the vector algebra here, is I would highly recommend that you draw a sketch, since this vector sum should exist. Now look at what we know. We do know the magnitudes and directions of both of these, don't we? Magnitudes and directions of both of these. And we don't know anything about that initially. So here's what you do, is you draw what you can. We know the velocity of B is scaled in that correct direction with a scaled value of 50. On the other side of the equation is the known 88 feet per second to the right. So what we do is we start here, and we go ahead and take this equation, or this known quantity on the other side of the equation. We start here at this pole and we draw it. 88. Relatively speaking, it's about like that. There's your magnitude of the velocity of A, the velocity of B. Now what must be true? You must go out to the tip of A and add to it then this relative velocity. So you go out to here and you now hook onto here, and you've got to come back up here, this direction. And that's the relative velocity of B relative to A, magnitude, and the direction shown. And you can see the parts. You can see the parts of this right here. Look at the math. Here is your 50 over radical 10 leg right here. The vertical part of it is the 150 over radical 10. And you can see that this relative velocity vector is made up of the net sum of these two quantities to the left. Clearly see it, to the left. And vertically from there upward. So this is a nice little scale, relatively scaled drawing of this. See it? See the parts? And it should fit together. It should fit with your vector algebra that you see. Do we know any angles in here? Do we know any angles on this drawing before we did the problem?
Yeah, we can find the angle of the right triangle. And
We
then
know
find
this
the
guy, don't we?
way- yeah.
We know this guy. So with this angle right over here now, this angle right in there, why don't we call it,
180 minus.
let's call it D. Angle D is going to be equal to 180 degrees minus the inverse tangent of 3 over 1. Somebody would punch that on the calculator for me. 180 minus the inverse in degree mode.
108.
Make sure you're in degree mode.
Yeah, 108.
About 108.4.
100 and what?
8.4.
Thank you. So angle D is approximately 108.4 degrees. So look at what we know here. Similar to the problem we had earlier today. Side, angle, side. Side, angle, side. So we could figure out the magnitude of this, again, using law of cosines. Let me write that up above here. Side, angle, side implies the velocity of B relative to A squared. If I square root it now, I'm going to have my sum of the squares of these other oblique triangle legs. Minus twice 50 times 88 times the cosine of that interior angle, 108.4 degrees. If you punch that out, I'm looking at this, I would estimate an answer probably a little bit over 100. Anybody have their calculator handy?
Oh, 138. Oh, I have the cosine one. I missed that one.
I got 102 and a half.
That might be.
102 and a half. So 102.5 feet per second. Have any of you had drafting experience? Most of you have taken the graphics course, right? Okay. So you all could use a protractor and straight edge with scaling and draw yourself a scale drawing here. And you could physically measure that and scale it, and you should lock in to a value pretty darn close to this. So that's a simple graphics way to do it, to an artistic side of things. Okay? And then you also could do the vector algebra and then find the magnitude coming off of this, hold it.
Yeah.
Something looks fishy. That's why your hand was up, thank you.
That's not right
Yeah, I think
because
it's 86.
Check this out, folks.
I did the magnitude taking that vector equation, got 114.
That sounds, see,
Yeah.
I hadn't looked down here, but see,
Yeah, I got
we went and tackled the problem another way, and somebody told me this answer, and then I hadn't looked back here. I come back and look at this, and I go, that thing's garbage, unless, or we screwed up over here.
No, he's right.
I've got that
What?
twice.
What's going on
It's 114.
up here?
Something went haywire up there.
Okay, we don't do that in engineering, do we? It doesn't go haywire. 114 point what?
0.1.
0.1. Okay. That feels a little better. That should, if you do square root of some of the squares here, you should get that result. Okay. Now, what if you had done this problem the way we just did it here with a little trigonometry? You've done this problem this way with a little trigonometry, but the question was, what's this vector? We have a little more work to do, don't we? We have a little more work to do. If I was looking for this vector, there's our magnitude. So what could I do if I know my 114.1? There's actually a variety of things. I know my 114.1 feet per second, but I don't know that particular direction very well, but I do have this picture. Couldn't I build a unit vector that points that way and tag it onto that magnitude? Okay, so we could take this thing that's 114.1 in length, and we could make ourselves a unit vector called V sub b relative to a hat, and that thing has to be equal to, doesn't it, this overall vector here with these parts shown divided by its magnitude. Now, you know something, that's going to be yikes. Here's what we were talking about doing. Figuring out this vector by taking and dropping in the 114.1 and multiplying it by a unit vector in that particular vector's direction. Okay? Now, the reason I said yikes is I'm looking back at this picture with my geometry here, and I'm going, well, why do that? Why take the time to figure out that unit vector since I already have the true vector's parts right here sitting in front of me in this simple description? So why don't we just go ahead and write it straight away instead as negative 50 over radical 10 minus 88 I plus 150 over radical 10 J. That seems like the easiest way to go at it, doesn't it? Okay. Okay. So the error that had existed here earlier, notice by tackling a problem more than one way, we're able to really quickly spot an error. If we just relied on this little sketch and done our work, we would have had possibly an error written down just because of not punching our calculator properly here. Okay. So hitting a problem a second way is oftentimes useful.